So I'm talking about 50-year-old work. And the work was done because it looked like an interesting problem. It involved some interesting mathematics, there was a challenge, and we didn't have the slightest idea that anything we were doing ever had anything, would ever have anything whatsoever to do with physics. We did the work, there was some controversy over it, it was ignored, and then it became important, and as all of you know, it appears to have become very important after the announcement on July 4th of last year of the apparent discovery of the long sought after standard model boson, or the Higgs boson. Now, so where were we at in the 1960s? Most of you, again given your age, probably think that was prehistory. But as it turns out, it was the dawning of the Age of Enlightenment as far as particle physics was concerned. We had a lot of the basic principles, the basic ideas that we currently use. We had sort of an understanding of the quantum theory of fields. We had many tools. The Schwinger action principle, which is essentially the same as a Feynman path integral. We had Green's functional methods of computing, and in particular, we had Feynman graphs, and mostly the only way we had computing was Feynman graphs. We did not have the marvelous power that we have today of taking an action, a description, and of quantized particle motion, and throwing at it a computer with any hope of getting any answer. One, because we didn't have a computer, and two, even after we had computers, it took a long time for them to get enough power to compute these problems. And even now, there's a very limited class of problems that you can calculate using finding out information about quantum theory of fields, because there are just so many degrees of freedom. The equations are nonlinear, and it remains probably one of, if not the most complex overall problem that one has to deal with in physics. Now, at the time of the 1960s, in the beginning, quantum field theory through perturbation theory had enormous successes. Namely, it had been used to describe the interesting and complicated spectra that were discovered after World War II when looking at the behavior of the various energy levels of light atoms. And when people first tried to calculate these things using the idea of quantized fields, all the answers were the same. Whenever you calculated anything at all that looked like it would be interesting, you got exactly one answer. Anyone know what that was? Infinity.
You know what Robert Serber said? He said just because it's infinite doesn't mean that it's zero.
Exactly. Sometimes it's zero. But anyway, renormalization theory is a technique which allowed you to essentially deal with the infinities, at least on electromagnetism. And it was unbelievably successful. You get absolutely marvelous numbers of it describing the energy levels of atomic systems. However, there are many other interactions that were known. For a very long time, people, of course, understood that there was a so-called weak interaction, an interaction which described the decay of a neutron into proton and leptons. And there was a theory that was very phenomenological in nature to calculate that decay. However, it only really worked to the first order because it did not meet the criterion of being renormalizable. So even though we knew how to calculate the electromagnetic interactions, we didn't have a clue as to how to calculate the so-called weak interactions beyond essentially the lowest order. Not only that, people were beginning to see so-called strong interactions, interactions that were characterized by having very strong couplings, very strong interaction between matter, and associated with very short-lived particle lives. And no one had a clue as to how to calculate these things because the coupling constants, the things that you could perturb in, turned out, no matter how you looked at them, to be large. So in the early 1960s, despite the phenomenal success of the idea of quantizing fields, people had mostly given up on making progress beyond electrodynamics using this method. And there were other methods that were under development, a technique called dispersion theory, S-matrix theory, and so on, which people believed had more hold. That turned out to sort of fizzle out, although it was very interesting. And it sort of had a brilliant reincarnation through string theory, but that's a whole other story. But people had given up, except at Harvard, University of Chicago, Imperial College London, and a few other places. People had given up on quantum field theory. It looked like it was the end. So in 1961, there was a major breakthrough made in discovering relativistic quantum field theory. It was made by Nambu and Yana Lucinio. And what they did was to look at a model that had a four fermion interaction. You could think of psi as describing a spin 1/2, and this interaction that I've written down there, G times psi bar psi squared minus psi bar gamma 5 psi squared, is a four fermion interaction, and it is not renormalizable if you try to expand it to try to solve it in the coupling constant G. You rapidly get infinities, and there's no way to control them with renormalization techniques, and it looks like approaching that theory through coupling constant expansions is impossible. However, Nambu and Yana Lucinio had another idea. They thought that perhaps there was another expansion scheme. And indeed, they figured one out. And that expansion scheme was very interesting because to get it, they assumed that things that would normally be zero, in particular expectation values of products of two fermion fields, things that we have the square of there, they assumed that some of those expectations, which by symmetry you would expect to be zero, were in fact some number. Now this was called breaking the symmetry, because Lagrangian had a symmetry. The symmetry led one, and that symmetry was reflected in the equations of motion, but one would expect, because of that symmetry, that all the answers that you got out of that theory would have that symmetry as well. That was essentially what you had learned from perturbation theory. Now, if we weren't so afraid of all this and thought a little about it, we would realize that we already knew with differential equations that you could write down a differential equation that displayed all sorts of symmetry and impose a boundary condition on the differential equation that did not have that symmetry and find solutions that also did not have the symmetry, although it was implicit in the overall structure of the solutions. But Nambu and Yana Lucinio studied this model, produced a seemingly self-consistent, in fact, a self-consistent model, which, by the way, happened to be not only different from perturbation theory, but in fact could be renormalized. And what this was, and is the first realization at least in these sorts of theories, of the fact the equations associated with that action are nonlinear, and and they're a nonlinear set of differential equations. In fact, an infinite set of differential equations. And you know perfectly well that you can look at differential equations and, as I mentioned, impose boundary conditions were not symmetric. This was a massive generalization of what people already knew, but we never thought of it before when we were looking at quantum field theory, because it was so complicated that it took Nambu's and Lassigne's imagination to go there. Now, as they worked this problem out, they discovered that there had to be a spin zero boson in the excitation spectrum of the problem. And in fact, they gave sort of a proof that that must be the case for this problem. So that was sort of interesting, and now a little worrisome, because there aren't many spin zero particles observed, and they thought that spin zero boson might have something to do with the pi meson, and so that was how they dealt with it initially. Pi meson is relatively light compared to all the other particles that we look at. This was again, let me stress, this is a real breakthrough. This solution in no way, even though you could write graphs for it, when you sum them up, they gave you a different solution. This solution in no way is related to perturbation theory. In fact, if you look at these solutions very carefully, you will see as the coupling constant goes to zero, that there are singularities in the solution reflecting that. That is, in fact, a realization of something that was suggested in a PhysRev Letters, I think, one-page article by Dyson many years before, where he speculated that the solution to the electromagnetic, essentially, that the solutions to electromagnetic equations were not unique. So this is a new solution. It's a beautiful concept, sort of a Platonic one, I think Weinberg has called it, where you have symmetries underlying everything in your basic theory. And they're there, but you can find solutions that don't have the symmetry. So beneath it all, there's some sort of hidden symmetry, and you can write down beautiful equations, but the solutions violate those symmetries, although in a way that has to be consistent with the equations. Now, what this did was that it demonstrated that the power of quantum field theory was essentially untapped by perturbation theory. It demonstrated that there was much more there. And almost immediately following that, Jeffrey Goldstone wrote another paper where, instead of having fermionic interactions, which were intrinsically non-renormalizable, he looked at sort of the prototypical scalar boson theory, where he took a charged boson and said it interacted only with itself, according to a coupling that went like 5 to the 4th of the boson, and he broke the symmetry. He assumed that even though the action was symmetrical under reflection of the scalar field, that the solutions were not. And he worked this out, and guess what he found? He found that there was a zero mass particle and a massive particle in the leading order approximation for this theory, and you can show that that persists as you go to higher approximations. So this business of having a zero mass particle was appearing to be a rigorous requirement of looking at theories in this particular manner. In 1962, Goldstone, Salam, and Weinberg very carefully proved that, for physicists, of course, since I see a mathematician here, for physicists, they very carefully proved that in relativistic theories, that if you have a spontaneous breaking of symmetry, a departure from symmetry in the manner that these two theories had, that you must always have a zero mass boson. This is a very bad thing because zero mass bosons are very easy to find. If there are a bunch of zero mass bosons around, you would expect them essentially to be running out of every physicist's ears, nose, whatever. So this was not a good thing. It made this new method look like it was problematic and maybe it was worth nothing to do physics with. Are they good for anything at all? Can you do anything with these when you have this problem? Very recently, Weinberg described how we all felt about it when this theorem was proved. And it is almost quote him. He compared the Nambu-Goldstone theorem, or the Goldstone theorem, as a requirement that zero mass particles is usually called. He compared this to the feeling that a small child has if when searching through his house, he finds a hidden cupboard that is filled with beautiful looking bottles of jam. And then as he is about to eat the jam, somehow or other he discovers the jam is poisoned. So we have a beautiful idea, seemingly an elegant idea, but it appears to be useless. However, there was maybe one thing that one could do with this. Julian Schwinger, one of the most famous physicists of the 20th century, had argued about this time, just shortly before this time, that there was no reason beyond the fact that the coupling alpha was very weak for the photon to whatever it couples to, electrons, for example. There was no reason that the coupling was very small and so that you could use perturbation theory. That was the only reason there was that the photon, the particle of light, had zero mass, but that in fact, if the coupling were stronger, there would be no such restriction. And then the question, no, by the way, I didn't believe this. I was a young graduate student at Harvard, and I had the nerve to think he was wrong. And I was wrong, as you will see. Schwinger was right. But the question is maybe there was still some way to use broken symmetry to write down a theory of electromagnetism that required, not just because of the size of the coupling constant, but required in general the dynamics made it necessary that the photon have zero mass. That would be nice, right? That you could actually say, you look at the theory and say, hey, the photon has zero mass. Well, this is where I came in. Berkane gave a talk at Harvard, and my thesis advisor was rather skeptical of his result. And he suggested that I look at Berkane's alternative model of electromagnetism, which was a variant of the Nambu-Young-Lacinial model. It had what's called a current-current interaction involving four fermions. Now, in order to use the Goldstone theorem for this, the Goldstone theorem is usually thought of as applying only to scalar particles, but that's not true. It can apply to particles of all spin. You have to work through it very carefully. But it is not restricted just to spin zero. That just happens to be where we use it these days. But Berkane suggested that we require that the symmetry of this interaction be broken and somewhat more than conjectured that it resulted in having theory like normal electromagnetism, where the photon was required to have zero mass by the Nambu-Goldstone theorem. Okay. And now the problem with this is the symmetry that's broken is Lorentz invariance. Now if you break Lorentz invariance, you can get into a lot of trouble because Lorentz invariance, even back then, was verified as being a very, very good symmetry of nature, at least on the scales that we're looking at things at. Now, what I did was I showed that his basic conclusion was correct, that you could break Lorentz symmetry, and that as it happened, that breaking in that model, because of its peculiar structure and the current conservation associated with it, it was benign. It didn't change anything you could measure. Now, that was certainly good enough for a nice PhD thesis, but I wasn't satisfied because I thought Schwinger was wrong, something Herb would tell me one should never do, but I didn't know then, I was just a kid. So I couldn't leave this alone. I thought, if this works for this model, there must be something like the Goldstone theorem that works for absolutely the normal electrodynamics that you have in Jackson that you just quantize. And so I started trying to find an example of this. I tried to find a Goldstone theorem which was valid in normal electromagnetism. And I tried very hard. And you know what happens when you try very hard? You succeed. And so I proved, in quotes, that there was a Goldstone-like theorem for normal electromagnetism, and therefore Schwinger was wrong. And my advisor, Wally Gilbert, looked at this and said, I don't know, I don't see anything wrong with it. I wrote up a chapter in my thesis and put it in the thesis, and I presented my thesis. Sidney Coleman, a famous executioner of bad physicists and bad physics ideas, looked at the thesis and looked up at me and said, and this is probably the first time he looked at it too, it was in the exam, and he said, I don't know, Jerry, I think this is wrong, but I don't know why it's wrong, but it's wrong. And there was a big discussion about it, and I was told to remove the chapter from my thesis. Fortunately, they let me pass. I was very lucky. So I just had to take the chapter out of my thesis. Now, as you can imagine, I didn't walk into my exam with a camera, but Sidney was very happy at once again having a logical triumph. And I can show, although this is a picture taken much later, this is what he looked like after the exam. He was in, what's that?
It flatters him.
Well, it was more impressive in a purple suit, which he wore to my exam. It was a purple velvet suit. So, anyway, that part I remember very well. During the time that I was at Harvard, I was talking to another fellow who I'd gone to undergraduate school with at MIT, and we'd worked a lot of problems together, and we in fact wrote our first paper together. And his name was C.R. Hagen, Carl Richard, but at the time everyone just called him Dick Hagen. And we did a lot of things together, and particularly physics, and we worked very hard, particularly on applied mechanics. And there we are at a working afternoon. You remember this scene? This is CEA, the Cambridge Electron Accelerator. And standing up, making what I assume is a friendly wave, is a man who became Baron May of Oxford. I'm sitting at the wheel of the Sunbeam Alpine, and looking all seemingly distracted and uninterested is Dick Hagen. Now, pretty much shortly after this picture was taken, a year or so, Hagen finished up ahead of me, and he got a postdoctoral position at the University of Rochester. Indeed, he never left. He's still there. And we continued collaborating. And we used to write papers, and the only way we could get stuff back and forth, this will be hard for many to believe, there was no internet. The mail didn't work very well. It worked. And we would send things back and forth on a bus. You know, and you'd pay the bus driver $20. If the bus was going to Rochester, he would carry a draft of the manuscript for you to Rochester. And that's how we did a collaboration.
$20 at that time is a lot.
Sorry?
$20 is a lot of money.
It was a lot of money, but I figured out how to charge it to DOE. You never called me. But we got some good papers out of it too. But anyway, Hagen, despite having seemed disinterested, became very interested in beautiful and expensive and very unreliable machinery. And because of that, he also learned how to minimize his living costs. And I thought he was gone, I shouldn't say it that way, but I thought he was surely going to become an experimentalist, not remain a theorist. And here he is in an early 1962 E-Type Jaguar that he bought just before he left MIT for University of Rochester. And that thing cost more than a year of his postdoctoral salary. And many times later on, I stood with him, panicked as we had the engine apart, because it was totally unreliable. You couldn't find anyone who would work on it at any amount of money that one could afford. But anyway, it's very beautiful. All right, I went off slightly after this to Imperial College in London. I had an NSF postdoctoral fellowship, and I was still very sure that I must be able to do better than I'd done with understanding gauge theories and why the photon had zero mass. As it turned out, CERN had rejected me. That was my first choice. I was very lucky, because it turned out Imperial College was just an unbelievable place. It was just fantastic. Harvard was good. Imperial College, at least to my perception at the time, was just much better. And they had a lot of very smart people there, and every physicist you'd ever heard of at the time all stopped by because London was a great place to visit. And so I got to talk to a lot of physicists. And the ones that I met who were there were Tom Kibble, Ray Streeter, John Cher, and Paul Matthews, and Abdus Salam, who ran the group. And they were really interesting people, and some of them still are. Unfortunately, it was a long time ago. This is Abdus Salam. He was nowhere nearly that serious, but that was his official, formal picture. He was actually a very easygoing and friendly person. And here, they worked hard at Imperial College, just like we did at Harvard and MIT. It's a picture of Salam with Tom Kibble. Now, so I was still worried, as I said, about why the photon didn't have zero mass. And I worried a lot, and as worrying will tend to do, as I pointed out to you, I then produced an absolutely beautiful, brilliant proof that the photon of normal electromagnetism must have zero mass through a Goldstone theorem. And after a while, I quickly wrote it up. I sent it off to PhysRev letters. Didn't talk to anyone about it. Probably should have. And I realized that after a couple of days, that it was just wrong. It worked beautifully for every case except the one that was most important. There's this problem in electromagnetism, as you mostly know if you're a physicist, that you have to worry about gauge invariance. And you have to pick the gauge you work in. And if you prove a theorem using the Goldstone theorem about electromagnetism, and it has to do with the vector potential, you'd better ask whether the theorem you prove tells you about the gauge parts of the vector potential or the actual physical parts that you can measure in the laboratory. Well, it turned out this theorem wasn't obvious at all at first. This theorem was absolutely true, at least if you looked at relativistic gauges, told you all about the gauge parts of electromagnetism. They had zero mass, which was totally irrelevant because you can't measure them anyway. But it said nothing at all about the physical mass of the photon. There was no content whatsoever in that theorem. Now, how could that be? There is an example then of the Goldstone theorem that if you had a relativistic gauge, told you there was a zero mass particle, but it only told you that the gauge modes were massless. And it didn't work in the radiation gauge, the gauge that throws away all the gauge excitation and just leaves the physical part.
Does that mean that the longitudinal and time-like modes were massless? But that the other modes could have mass?
No, the transverse modes, there was no statement about whatsoever.
Oh, right.
Okay, what that meant is that they could be massive or massless, and there was no way to tell from this theorem.
Okay.
And by the way, that's exactly what happens in standard model realization, right? Where you give masses to the W's and the Z's, and the photon stays massless. So this theorem really was important in understanding all this. And you know, obviously, the Goldstone theorem, you had to be careful about how you applied it. And it certainly was wrong when you applied it to gauge theories, and you didn't sort out physical from unphysical modes. And
let me ask, I don't mean to judge you, but the way we used to say it is that the massless mode develops mass because you have a long-range Coulomb interaction, which is a result of the gauge theory.
This is all related, of course, to what you've said. A lot of it gets obscured because we had to work with theories that were, in the end, relativistically invariant, and that was what made it hard. And it hit a lot of stuff. I can now, and you can easily say, hey, you shouldn't worry about that. You should ask how it all worked. But remember, we were woefully ignorant. We barely had heard of superconductivity.
No, but I'm just trying to make the connection.
It's
non-relativistic theory.
Non-relativistic theory. Now what happens? Why does the theorem fail? Why doesn't it give you any information? Turns out that the charge, you have a conserved current associated with this. I'll show you what that particular current is for this. It's a strange one.
Yeah.
But you have a conserved current that you use for the Goldstone theorem. And so you have partial mu of this conserved current. It's not the normal current. Partial mu of this thing equals 0. And so what would you say? Immediately you would say, the integral of the time-like component over all space is conserved. However, you're forgetting something. Partial mu j mu equals 0 only tells you that the time derivative of the charge vanishes if the integrals of the spatial parts at the edge vanish. In this case, they do not. And so there's always charge leaking out. Yeah. And that is why this Goldstone theorem does not work for any kind of gauge theory. This is an absolutely general result. Doesn't matter whether it's Yang-Mills or whether it's E and M. I'm sorry, I got technical, but I have a real expert sitting in the front. So. All right, so it was clear to us that there was a brand new game to play. I figured out, I caught this error after a couple of days after I sent the paper off to be published. And realized the magnitude of this, why it was important, and why it was wrong, and what it implied. It was a revelation, along with a sinking feeling in the stomach, and my heart went down to there, because I'd sent off my first paper to Phys Rev Letters, and it was totally wrong. And I wasn't terribly worried. Now, it took a long time to get published because of postal strikes and things, and I put it in the mail, and it sat in some post office in London for months, apparently. But I wasn't worried, because at those days, the paper, even if it was accepted, the papers were typeset and sent back to you to approve the typesetting. You remember those days?
Yeah.
And I figured, all right, I'll fix this in the typesetting and I'll make it right. If it goes through the referee, if the referee rejects it, I'll fix it then. through a series of incidents that are totally unlikely, I never saw the paper again. It got published. But this was an important paper because it was a key to this whole issue of why there is what's now called a Higgs boson. Now, Peter Higgs, who was working in Edinburgh, who I'd never met, didn't meet till later, never even heard of, sent a paper off to Physics Letters. I don't know when he sent it. It was received July 27th of 1964, much later than my paper turned out to be published. And guess what? He had made the same subtle error. Now he didn't go through the proof the way I did. He just looked at a spectral representation and said, hey, this spectral representation looks funny in the radiation gauge. There must not be any Goldstone theorem. Well, what he did, now he didn't make a subtle error. He made the same subtle error I did, and then he interpreted that subtle error wrong. So he concluded that there was no Goldstone theorem for gauge theories, which of course, that conclusion is correct, but the way he got it was wrong at every step. But that paper, I should mention, is very, very famous. And the error is quite subtle. You know, even now people don't understand this. And, you know, because people haven't worried about it for a long time, this is just beginning to surface again. All right. Now, I'm going a little too slowly, but let me just point out to you on this slide, this thing here, this two-component tensor, you'll notice is just F mu nu, the electric and magnetic field, if there's no charge. Now it turns out if there's no charge, if J mu equals 0, that F mu nu, of course, partial mu of F mu nu vanishes, and so F mu nu behaves like a tensorial current that's conserved. And the commutator of F mu nu with the electromagnetic potential A is non-vanishing. And so you can prove, for a free electromagnetic field, you can prove a Goldstone theorem. And so for a free electromagnetic field, which has zero mass, you can prove it has zero mass. So it's all consistent. However, everything changes if you allow an interaction. This current that I've written down, very asymmetrical, right? Funny looking current. Nevertheless, it is conserved. Just follows immediately from the equations of motion. And therefore, if you were naive the way I was, you would immediately assume that there are a set of four objects which have vanishing time derivative. However, you can also, you can also look at the commutator of this so-called current, the set of four, with the electric field and show it's a non-zero constant. That's your Goldstone theorem. You can easily show that this implies that QK must, in particular AL, must excite a zero mass particle. However, you can go through this argument. You can use what are called spectral representations. You can prove in general, without using any sort of perturbation theory at all, just using the properties of the theory, that QK is when it's commuted with anything, never produces something that is independent of time. This charge is not conserved, and therefore you can go on and reason that there is never anything like a Goldstone theorem. There's never any dynamical reason to have a zero mass particle for any theory involving gauge particles. So all this argument is very easily generalized. There is no Goldstone theorem for any theory that has electromagnetic or Yang-Mills interactions. And that was, and I'll skip the details of this. Okay. So, as I said, this is an exact observation. Now, what is interesting about all of this is the fun part of this, maybe, or amusing part. There has been a tremendous reawakening. I don't know if tremendous is the right word, but there's been a reawakening of all this. And physics now, as you probably know, is done not only in published papers, but it is a lot of blogging. And there's been a lot of commentary in physics blogs, well, many of them by reputable people, some of them not, in my opinion, but many of them by reputable people, discussing our paper in particular. And many of the things that have been said are having to do with the scuffling for credit that is going on, particularly in Europe. At this, we haven't responded until now. I'm now responding. So there has been a lot of claims made about our paper which are utter rubbish, and I will address some of them as we go on. Now, to do that, let me point out the exact differences between our paper and two other papers that were published about the same time, although slightly prior to our paper, in Phys Rev Letters. One by Peter Higgs. This is after his Physics Letters paper that I mentioned already. And the other by Englert and Prout. Okay. Now, only our paper explains this mechanism I just talked to you about, which has come to be known as the Higgs mechanism. The Phys Rev Letters of Englert and Prout and Higgs do not deal with the Goldstone theorem at all. To Englert and Prout's credit, they mention it, but they don't deal with it. They say, this must be a zero mass particle around somewhere. They don't have the equipment, the way they set their paper up, to actually look for it. They only look at essentially one graph to reach their conclusions, which are partially correct in the model that they look at, which is related to our model. And Peter Higgs gets it wrong in his Physics Letters paper, as I just mentioned, and he also gets it terribly wrong in his Phys Rev Letters paper, and I'll tell you why in just a minute. So, now the point of all of this is a major problem. The problem that we were trying to solve was why did the Goldstone theorem why was it not an obstacle for looking at some physics? Why was it possible to have symmetry breaking theories that had content where a zero mass particle was not required? And the result I just mentioned is the reason. And so what we had done is shown that at least, and this is a big at least because this is the theories we're interested in, that in electromagnetic-like theories and gauge theories, that there was no Goldstone theorem. You could break a symmetry, but the results were not constrained by any theorem because of this business of the charges leaking out of any physical volume in the radiation gauge, and where there wasn't an issue of leakage, where you looked at a fully relativistic case, the Goldstone theorem only told you about non-measurable gauge excitations. Okay. So, now, having done that, having proved this general theorem, we wanted to find a special case where we could actually see a photon having mass. Now, there had been a previous example, which I'd mentioned. Schwinger had shown in 2 dimensions that there was no zero mass photon. However, I just said something wrong. There is no photon in 2 dimensions, right? The reason is, in 2 dimensions being one space and one time. The reason being that you can't have E and H with a propagation direction perpendicular, T and H. So 2 dimensions, or one space, one time, is really just gauge. So his theorem is certainly correct, but it is rather different than looking at a system where there's actually a dynamical photon, although you can fit it into this category I've just described. Be careful now. So what we did is, we thought, all right, we knew that there had to be, from my experience looking at 4 fermions, theories, we knew that there should be more than one solution to normal electrodynamics. And so we wrote down the action for normal electrodynamics. Now this is probably not familiar to you because it is written with phi being a real field, and normally you write phi as being phi and phi star. It's a complex field, but we divided things up into their real parts, so we just replaced everything where you'd have complex fields by matrices, column or row matrices of having two entries. And we treat phi mu as an independent parameter, but this is exactly your normal Lagrangian for scalar electrodynamics, although you'll notice there's no mass term for the scalar particle in this Lagrangian. And furthermore, you will notice if you have done electromagnetism and you look at the conventional books and they talk about renormalization. Now renormalization is different in symmetry breaking cases than in non-symmetry breaking cases, but nevertheless you have to do it. But you'll notice if you look in the text that you'll usually see a phi to the fourth term written in scalar electrodynamics. And a phi to the fourth term is essentially a counter term because when you figure out graphs, you would generate things that are equivalent to phi to the fourth interactions, and they figure into the renormalization. However, it was the habit at Harvard, and Schwinger's in particular, never to explicitly include the counter terms. You never wrote them down in the basic Lagrangian. When they occurred in the calculation, you just dealt with them. By the way, a very good way to do things when you're doing lattice gauge theory, because you can get in a lot of trouble with lattice gauge theory if you put those terms in, because lattice gauge theory is always done, in a finite dimensional box, and then you examine the limits. So you don't really, so we have never put those terms in, but the convention is to put them in. So we didn't put them in. Now we want to look for solutions that violate the charge symmetry, because it has a conserved charge. We want to break it. And so the natural way to do this was to require that the expectation value of phi was non-vanishing. You'll notice that the action always has both a phi and a phi mu in it, and phi mu, you can easily convince yourself that this thing is symmetrical under reflection of phi, or if you wish, some reflection of phi and phi mu, that is equivalent. So this thing has a symmetry under reflection, and requiring that the vacuum excitation be non-vanishing breaks that symmetry. So we look for such solutions, and I did it the hard way, because I had done this Barricade model. The Barricade model just sort of rolled out the whole thing with sources and sort of produced every order of it. And you had to figure out how, one, what the first order approximation was, and then how you iterate upon the first order approximation. And that was pretty awful, and no one was going to ever look at that. I never published it, I should have. But anyway, so we figured out an obvious and simple way to pick out the leading order approximation. Everywhere we saw phi, we just replaced it by a C number, so we could reduce the equations of motion to these simple linear forms. And you can solve these linear forms. And when you solve them, fixing them so they're diagonal, just making your definitions appropriately, you lose nothing from that. You see that one of the scalar fields, phi 1, you see there, is characterized by a mass term. Phi 2, the other scalar fields, has zero mass here. And what was the electromagnetic field, the transverse part of it, is also characterized by having a mass. That mass is not zero. It's some non-zero number. Now, so phi 1, if the Goldstone theorem were true, would be required to have zero mass. So this is immediately a violation of what you expect to be true. So now phi 2 in our approximation has zero mass, but there's nothing saying that it has to have zero mass. There's no theorem constraining it or anything. It's just a leading order approximation. Now, this is different from the solution. Again, let me skip this. A big fuss has been made about this. This is different than the solution written down by Peter Higgs. In his paper, phi 2 is multiplied by a term that looks like it has a mass. Now, that mass is arbitrary. It involves an undefined coupling constant and an undefined vacuum expectation value. And by tuning the expectation value and the coupling constant, you can make that mass in Peter Higgs's theory be anything you want. But it doesn't matter, because these are all leading order approximations. All these masses are subject to renormalization. When you calculate the higher order corrections, there are divergences. And it changes these masses, and the only thing that is important is none of them are constrained to be any number at all. They're free floating. Now phi 1 is the excitation that is associated with the so-called Higgs boson, or the scalar, the standard model boson. Now, as you know, it was a big problem to figure out what the mass of the standard model boson was. There were conjectures, there were ways of confining it, but you certainly would, just on general grounds, expect it to be less than 1,000 times the mass of the proton, because otherwise the theory begins to look silly. But there are really no constraints. These are real field theories, these are not phenomenological field theories, and there are really no constraints at this level, or any other level for that matter, as we know the theory so far, that put any constraints on that mass. Now this has actually been argued in the London Times by some people who claim that our paper was wrong because of this, and have no, the person involved, as far as we can tell, has no understanding whatsoever of mass renormalization, of how these things work. The fact of the matter is, why is Higgs's paper different from ours? Because Higgs puts in an explicit 5/4 interaction in his Lagrangian. That makes the Lagrangians look superficially different. However, if you calculate to higher and higher order, these two answers converge to the same structure. And again, with undetermined mass for the Higgs boson. Anyway, so this has been a source of argument. Now, the paper by Englert and Brout does not display the Higgs boson at all. It's got to be there, but again, because they just worked out some of the model, there's no discussion of it or no equations for it whatsoever. Again, I'm going much slower than I should have. I just mentioned again, if anyone doubts what I say, you can check it, because this is what physics is about. We can check things exactly. And there's a paper by Coleman and Eric Weinberg. And that paper essentially gives you a calculation of all the integrals you need to calculate to show that our Lagrangian and the Lagrangian written down by Higgs converge to the same answer. All right, now let me just summarize. Okay, we address two major issues. We show exactly why gauge theories do not require zero mass particles. This is model independent. We can prove it by looking at general spectral representations. And what we do is a fully quantum proof. We also then give, independent of this, but consistent with it, a separate model where we do non-coupling, which is electromagnetism, but we look for another solution other than perturbation theory. And we do a non-coupling constant leading order approximation to that model. We did this shortly after I wrote my wrong paper. But we didn't send it off for quite a while because at this stage we were all very scared. I had made 2 major errors, 2 strikes. You know what happens with the 3rd strike. You don't get a job. And so we really wanted to have a much more general understanding of this. We ran every check we could think of. We talked to a lot of people. All the people that we talked to said it was baloney, by the way. No one believed this, because part of what we did was break gauge invariance, but we respected current conservation. But finally, we published it, and as we published it, we found out that there were 2 other papers, the ones in Phys Rev Letters by Higgs and England and Brock. Again, the paper by Higgs is actually wrong, again, because he does not deal with the Goldstone boson. His paper, if you look at it, he works it out. His solution is written down in an arbitrary gauge. He doesn't fix the gauge. In an arbitrary gauge, you must have a 0 mass excitation. If you look at his equations, you will see that they actually have what corresponds to a 0 mass solution to them. But he doesn't write it down. He only writes down the massive solution. Now, technically, since he claims he's only doing things classically, you could leave that term out. You should say you're not writing down the most general solution to the equation, but there's nothing, there's nothing that says the term with 0 mass has to be in it. However, if you do it quantum mechanically, which then you must do because the Goldstone theorem is a quantum mechanical thing. It sets boundary conditions on the equations of motion having to do with commutation relations. If you do that, you see that the commutation relations absolutely require that you include in his problem the 0 mass excitation. He just leaves it out. All right. So, just go on to conclude. There are 3 more papers in this series. Remember, there is my original paper, the first one in the series, but certainly wrong. Higgs's paper in Physics Letters, wrong. The 3 papers in Phys Rev Letters with varying degrees of correctness. And I would claim ours is entirely correct, except for the very last formula, where there's a consistency check, and we forgot to take the real part of the equation. So that's embarrassing. We didn't realize it until a year ago. But anyway, I gave a talk on all this, somewhat similar to the one I just given, although much more technical, and I hope this wasn't too technical. It probably was. But I gave a talk on all this at Edinburgh University and Cambridge and a bunch of other places. At Edinburgh, Peter Higgs was in the audience, and this was after the papers were published, very shortly after it. And then in the summer, I gave a similar talk at a conference in Feldafing, Germany, that was essentially celebrating Heisenberg's appointment to the directorship of the Max Planck Center in Munich. And Heisenberg heard my talk there, and I talked to him afterwards, and he made it very clear that he held the results and the idea in very low esteem. I was very scared, to say the least, because I thought that was the end of my career, and he was not alone. But when Heisenberg tells you you're wrong, and he doesn't seem to be uncertain, you know you're probably But anyway, I wrote, that paper was published in the proceedings of that conference, It's available at rare book dealers now. And recently it was republished and it's posted on the archive. And then after that, Peter Higgs in 1965 put a paper in Phys Rev, which is very similar to my Edinburgh talk, and he acknowledges conversations with me. And he adds one extra element to the paper. He displays tree graphs, which contribute to the next order of the calculation of this model. And finally in the series, Kibble by himself wrote up our analysis as applied to non-abelian gauge models. Now, as I pointed out, the analysis is the same whether you look at abelian gauge models, E and M, or non-abelian gauge models. We knew it at the time, but it was certainly worth writing a paper on. And he did write it up, and that was published in 1967. Now, we were fortunate that 6 of us got the Saccharide Prize in 2010. Peter Higgs didn't show up, so he didn't get his picture shown. On the left is Tom Kibble, and then myself, then C.R. Hagen, Englert, and Brault, who sadly did not live to hear the results of July 4th. Now, as this was all going on, particularly as we wondered whether we should publish or not, Kibble and I tried very hard to get inspiration by emulating Einstein. And here are pictures of us looking for inspiration. And that's the